In this video, I'm going to be covering how to calculate the net force in 1 and 2 dimensions. This is part of topic 2.2 of the IB Physics Syllabus. It's relative then to HL and SL curriculums. Please take a moment to read the success criteria I plan to cover in this video. Take a moment and brainstorm some of the types of forces that you might already know. How about a push or pull, sometimes called an applied force? What about the force due to gravity? Now, I will be specific here because if you just say the word gravity, you could be implying acceleration due to gravity. There's also friction, the normal force, or sometimes called the reaction force, why you don't sink into the chair you're sitting in right now. Here are a few more. Nuclear force, which could be the strong force or weak force. We'll talk more about that in topic 7. The electrostatic force between charges, or the more general phrase of electromagnetic forces, which also obviously includes magnetism. Tension in a string, elastic force in a rubber band, air resistance, sometimes called drag. There's lots of other different types of forces, and we could be using any one of these in our force diagrams. So let's start off with talking about free body diagrams. Now I've got a block on an inclined plane here, and so let's first just start off by drawing the different forces on here. I could have the force due to gravity, which we usually draw from the center of the object, straight down. And we could also have the normal force, or the reaction force, why the block isn't sliding into the surface. We usually draw that perpendicular from the surface. That's why we call it the normal force. It's perpendicular to the surface. If I had friction, I could add force of friction. Remember, if I draw it like this, that's implying that this block is going to be trying to either slide down the ramp or it's sitting there. If for some reason the question was the block moving up, then my friction would be drawn from the other side. No matter what, friction is going to be parallel to our surface. Now, all of these forces drawn on my diagram here are great, but they're showing from different spots. And if you do topic B1, which talks about rotational motion, that does make a difference. But right now, we're going to assume that they're all acting on the box, and the box is like a point source. So if I draw a free body diagram, technically what we're looking for is this. Let's draw everything starting from one single spot. That technically is now a free body diagram. Now, let's look at the forces acting on this block. As it's sitting here, I'm going to have a force due to gravity. I have a normal force. And in this case, I'm having a force pulling it along. And notice we're being a lot more specific. It's at 42 degrees. So now, when I break it up and I write it in, I'm not just going to randomly put some pieces in. I'm going to have to be very careful about how I draw them. In the next slide, I'll talk about breaking this into its components so we can start talking about how these forces affect each other. Because you can see now that yes, I've got the force due to gravity straight down and the normal force straight up, but I have this other one and it has pulling it a little bit to the right and a little bit upwards, and we'll see how it affects everything together. So the way these vectors work is that if this is being pulled a little bit to the right and a little bit up, I can break it into what we call its components. How much is vertical and how much is horizontal. And for this, we're going to use trigonometry. So if I'm looking at this one, and I'm going to put a little v for vertical, over here we'll put h for horizontal. Compared to the 42 degrees, you can see that this one is the opposite angle. Here's our hypotenuse and opposite. So if I want to calculate the force that's vertical, I have here, I know my opposite and hypotenuse. Trigonometry, opposite, hypotenuse. Right, that's sine. So sine 42 must be my opposite, which is the force vertical, over the hypotenuse, which is the total force. And if I rearrange that, my vertical force will be my force times sine 42. Now, if you want to do that for the horizontal force, now we've got the adjacent side. And so I can do the same idea, except for now it's going to be cos. So cos 42 is going to be adjacent, which is F horizontal, over the force. And if I rearrange it, F cos 42 degrees. Now you can also measure this angle here from the vertical, and then you would have had F sine 48. So there's more than one way to use our trigonometry here. So translational equilibrium, big fancy term that says translational, left, right, up, down in a straight line, not rotating, and equilibrium means nothing's moving. So everything is going to be balanced. Let's first look at the black box. We have a force due to gravity pulling down on it here, and we must have tension in the rope pulling up. Remember, ropes only pull. Ropes or strings cannot push. So in this case, if nothing's moving, that means my forces must be balanced. And if you remember, the length of the arrow should indicate the magnitude of the vector. So if I do the free body diagram here, I should have force due to gravity pulling down and tension of the same size pulling up. There's my free body diagram for the black box. Let me draw my diagram, or my forces, on the gray box. Still force of gravity pulling down. If I have my normal force pulling up. I also in the last picture said about force of friction. Now in this case, I would suggest that the force of friction is stopping it from sliding upwards, so it should be drawn in this direction. I still have one more force to put on there. Do you see what it is? That's right, it should be tension in the string pulling this way. Now one other thing to think about with the string is the tension has to be the same throughout the string. You can't have one side pulling more than the other. So these two tensions are going to be exactly equal. The only thing that's changing in this case is its actual direction. Now if I've drawn my free body diagram right, it should look like this. Let's think about what I've tried to do here. First of all, if it's in translational equilibrium, then vertically and horizontally my forces should match. So I have my force due to gravity pulling down here, and I have a little bit more from the vertical component of my force of friction. Upwards, I have a component of my normal force and a component of my tension. Now that was like a lot of three things I had to break into components. But a lot of the times what we will do instead of that is we will talk about, instead of horizontal and vertical, we'll talk about F parallel and F perpendicular. And that is in reference to the plane of the incline. So now let's think about how much we have perpendicular to our surface and parallel. Notice now the only one I have to break into components is the force due to gravity, and I can break it into the part that's perpendicular to the surface and the part that's parallel. And I've tried to get it so that if I add this one and this one together, I should get here. And if I've added this one and this one together, they should balance out. It's a little hard to do on the computer. Okay, so let's look at some examples. If we take a look here, we have an athlete running and it tells us we're working at a constant velocity. Now that's really important because Newton's first law says if all forces are balanced, an object will travel at a constant speed. So we need to have all of our forces balanced both vertically and horizontally in order for this athlete to be traveling at a constant speed. So let's take a look first of all. It cannot be d. because those forces cannot get balanced. This would be accelerating backwards. In other words, probably slowing down. If I look at some of our other ones, here in A, we also can't have it balanced. Let me just back up that for a second. Take a look. Horizontally, it's balanced. But that normal force right here, there is no way that that is going to be able to balance out our weight. Oh, but it also has a horizontal mark. So, no. All right. Now, if I break this normal force here into components, it might be possible. But let's look closer at what these forces are. We have the normal force, that's the contact force, and we have weight, W, and R and F. Now, let's think about this a little bit more. If we have air resistance, that's going to be moving this direction because he's shown running forwards. And now we got to think about the normal force. Is it in the right direction? Well, if you recall from before, I said the normal force always acts perpendicular to the surface it's in contact with. So this one's not going to be correct. Yes, he's pushing down on an angle, but we from that get these two forces. Force of friction will be pushing us forward and the normal force pushing us up. So in fact, his applied force on the ground would be in this direction, this way. We also know that the force of friction is actually going to be pushing him forward. Let's think. If you're walking down the street and it's icy, you can tell very quickly if it's slipping or not. And that's because when you push back on the ground to make you walk forward, that force of friction isn't there anymore, which is why your foot will slip. In this case, the correct answer is B. An object of weight 15 newtons, and yes, that is correct. Weight is the force due to gravity, so it's measured in newtons. If it's a mass, it's measured in kilograms. This is one of those times where everyday English and science don't actually mean the same thing. So an object of weight of 15 newtons is pulled along a horizontal surface at a constant velocity of 2 meters per second. The force pulling the object is at 12 newtons at an angle of 30 degrees to the horizontal as shown. What is the force of friction? So let's go through and think on our free body diagram which ones are going to have to balance in order to get our constant velocity. Okay, so I have my force of gravity pulling down, and pulling upwards or pushing upwards would be the normal force and the vertical component of that applied force. Horizontally, I have the force of friction. It's going to have to be to the left because we know friction always opposes the motion, and the horizontal component of the applied force to the right. Again, it tells us this is a constant velocity, so we know that all of our forces must be balanced. If I'm looking for the force of friction, then it's going to be the horizontal component of my applied force. I've just said FA for applied force with a little subscript H to tell us it's the horizontal component. Now, if we take what we've done before, this is going to be 12 and 30. Horizontally is going to be adjacent to that 30, so it's going to be cos. And when I put that in my calculator, I get 10.4 newtons. Okay, so here's one more block on an inclined plane. And in this case, it tells us that the friction is negligible. So I have all the forces already drawn on here. We have our force due to gravity or our weight and the normal force. Now the block is sliding down the slope. So it's asking for the resultant force, and it's going to be then along the slope. This is one of those times where it's better to talk about parallel and perpendicular to the surface than it is vertical and horizontal. So if I do that, we're going to have the W parallel here and W perpendicular here. The diagram is also very nice to us, and it tells us this angle here is theta. You can extend this. Let me just point this out. If I have 90 degrees here, we have theta plus, let's call this x. in our triangle, so theta plus x in the 90-degree triangle, so theta plus x must equal 90. And if you take a look here, this is also going to be x. And again, theta plus x equals 90. So that's why this angle here has to be theta. Okay, so we know that this one is going to have to equal this one because it's not accelerating off the surface. It's going along the surface on our way down. And what will be the resultant, or the net, or the overall force on the block? It's going to be W, the weight, parallel to the surface. And if that is parallel to the surface right here, okay, that is not adjacent to my theta. It is going to be this side and this side of the rectangle are the same component. So this is going to be a sine. Therefore, my answer is going to be A. So please read through the success criteria one more time. I hope after watching this video you can say I can to all these statements.